Hello and welcome to this video on the volume of pyramids, cones and spheres. Now let's just say you had a prism like this. Remember, prism is just a 3D shape that wherever you chop it, you would see the same shape, which we would call the cross section. So in this case, wherever you chop it, you would see a pentagon. And in the previous video, we saw that the volume of a prism was just the area of the cross section, so that shape there, the pentagon, times by the height. And let's say you were a sculptor and you were to sharpen this prism so it formed a sharp point at the top. Now what would you guess the volume of this is relative to the volume of this? Obviously it's going to be less because you've removed some of the volume when you sharpened it. You might think it's half, but in fact it's a third of the volume. So the volume of this pyramid here is going to be equal to a third times by that area, which we can't really call the cross-sectional area anymore because we see a different shape if we sliced it at different points. So we're going to call that the base. So this is the base, so it's a third times the base and times by the height. So it's a third times the area of the base times by the height, and that is the volume of a pyramid. So we do this first question here, question 1. We've got this pyramid here with a square base and the height is 8, and these are all in centimetres. Now the volume would just be a third times the area of the base, which in this case is a square, so it would just be 10 times 10, times by the height of 8. And if you put that into a calculator, you get 266.7 centimetres cubed. It's centimetres cubed because we have a volume. Now we've got other 3D shapes as well. We've got a cone, and the base has a particular radius, and again it has a height. Now can you see that a cone is just an example of a pyramid? It's just a pyramid that has a circular base. So we can use this formula for pyramid, can't we? So the volume is equal to third times by the area of the base, that area there, and the area of a circle is pi r squared. And then it's times by the height, which is h. So therefore, the volume of a cone is equal to a third pi r squared h. But I don't bother to remember that one. As long as you can remember the volume of a pyramid, and you can remember the area of a circle, then you've got the volume of a cone, haven't you? And the very final formula is the volume of a sphere. And if you've got a radius r, the volume is equal to 4/3 pi r cubed. And that will be given to you in an exam if you ever have to find the volume of a sphere. So let's use that to answer these questions here. We've got a sphere here with radius 5 centimetres. So the volume of that, if we just use this second formula here, is equal to 4/3 times pi multiplied by the radius cubed, which is equal to 523.6 centimetres cubed. What about B? This time we've got half a sphere, which is known as a hemisphere. And we're going to just use exactly the same formula, except we just need to half the volume. So we would define the volume of a full sphere first. It'd just be 4/3 times pi times 11 cubed. And that gives you 5575.3 centimetres cubed. But we want half of that, so we just need to do 5575.3 divided by 2. So I'm going to type divide by 2, and that gives me 2787.6 centimetres cubed. And some of you may have spotted that instead of doing 4/3 pi r cubed, we could have just done 2/3 pi r cubed, and that would have given us the correct volume immediately. Next we've got a cone. So we've got a cone with radius 3 centimetres and height 12 centimetres. So we can just use the formula. The volume of the cone was a third pi r squared h. I will write it out again for you. And if we just plug in the numbers, we got a third times by pi times by the radius squared, which is 3 squared, times by the height, which is 12. And we put that all into a calculator. And that gives us 36 pi, or as a decimal, if we press the SD key, it gives us 113.1 centimetre cubed to 1 decimal place. What about B? Now this one's harder. We actually got a cone with the top part of the cone chopped off. And that's actually known as a frustum. So this is called a frustum, probably the most amusing sounding mathematical word. So we can imagine that there is a kind of cone being completed here. And the way we can find the volume of this frustum is to start with the volume of the whole cone and just subtract that sort of imaginary cone at the top. And that would leave this volume here, wouldn't it? So let's find the volume of the whole cone. Now notice, by the way, that this radius is getting 3 times bigger to get to here. And that means this height here of the cone must be getting 3 times bigger to get to the height of the full cone. We've got this idea of scale factor. So that's 3 times bigger to get to that. The height of the small cone must get 3 times bigger to get the height of the entire cone. So what times by 3 makes it 8 bigger? Well, it would actually be 4 centimetres. And let's just see this. 4, if you multiplied it by 3, it would give you 12. And you can see 4 plus 8 is indeed 12. So that would be right. So let's find the volume of the whole cone first, the whole thing. That would just be 1/3 times by pi times by the radius squared, which is 9 squared, times by the height, which is 12. And that simplifies to 324 pi. I'll leave it in that form for the moment. And then the volume of the code that we're discarding, this top cone here, that is 1/3 times by pi times the radius squared, which is 3 squared, times by the height, which is 4, and that gives us 12 pi. And that means the volume of our frustum that we want is going to be 324 lots of pi minus 12 lots of pi, and that is going to be 312 lots of pi. And that, as a decimal, would be 980.2 centimetres cubed to 1 decimal place. Now finally, we've got this question here, where we're told a solid sphere radius r here is melted to form a cone of radius 2r and height h. Determine h in terms of r. Now if something is melted, then the volume is preserved, the volume stays the same. So we could find the volume of the sphere and make it equal to the volume of the cone. So let's do that using the variables here. So the volume of the sphere is 4/3 pi r cubed, and the radius there is r, so we can just use r. And that is equal to the volume of the cone, so that's 1/3 times by pi times by the radius squared, so it's 2r squared. Notice I'm using brackets around the 2r because I want all of 2r squared. If I didn't have the brackets, only the r would be squared, not the 2r. And we're timesing that by the height. Now let's just simplify a bit. Well, 2r squared, 2r times 2r is 4r squared. So it's 1/3 pi times 4r squared times by the height. Let's simplify further. Well, 1/3 times 4 is 4/3. So we got 4/3 pi r squared h. Now, I don't like fractions in my equation, so I'm going to times both sides by 3. So we get 4 pi r cubed is equal to 4 pi r squared h. And then let's see what we can divide by. Well, we can divide both sides by pi. We could divide both sides by 4. All we're left here with is now r cubed is equal to r squared h. Now h is being multiplied by r squared, so I divide both sides by r squared. And r cubed divided by r squared is just r. So it turns out that the height is just the same as that radius there.